So, here's my example. Right? First of all, I need to find my stationary point. Now, I know we did this example, so first of all, nice and easy, just differentiate it. So I get 2x plus 6, okay? And then, of course, my stationary point will occur when dy by dx equals 0. Happy with that? So I set this to be 0, I get 2x plus 6 equals 0. I find x is equal to, what is it, negative 3, okay? What was y equal to again? Can anybody remember?
Negative 4.
Negative what?
4.
Negative 4, okay? So in other words, my stationary point is at negative 3, negative 4, okay? But here's where it gets interesting. If I want to find my maximum or minimum, is it a maximum or minimum, then all I would need to do is take this and differentiate it again, okay? So if I want to find, is it a max or is it a min, I differentiate it again. Good, so if I differentiate this, what do I get? 2. Okay. Now you ask yourself the question, is this positive or is this negative?
This is negative.
2? Yeah, 2 is positive.
No, I mean it's
I know what you mean, and that's exactly what I'm trying to say, yeah. A little bit confusing, right? Yeah, so because 2 is positive, that means that my rate of change in my gradient is positive. Well, look, over here. When the rate of change of my gradient is positive, it means my function is increasing. So as I move from left to right, my gradient is getting bigger. That can only occur at a minimum. Okay? So therefore, this point here, my stationary point, is a minimum. Does that make sense?
Well, we already know that because the coefficient of the...
Because we could... yeah, exactly, because you know something about quadratics. But what I'm trying to say here, what if it was a cubic, or a quartic, or a quintic? Like a really hard differential equation, or a much longer equation to start off with, which you didn't know how to sketch. The point is, with this process here, you don't have to sketch it. You don't have to sketch it. You can find the stationary points, and you can find where their maximum or minimums. Does that make sense to everyone? Yeah. Okay, good. Now, Archimedes, you're right, it's confusing. Okay, it's the opposite of what you think it should be. Because let's pause. When it's positive, it means it's a minimum. Doesn't seem right, does it? But of course, if you think through the ideas, it does make sense. Okay? So the way which I remember it, now I know these ideas, the way which I remember it is it's the opposite of what you think it should be. If it's positive, it means it's a minimum. If it's negative, it means it's a maximum. Okay, so second derivative.
What if we, even if we like get another derivative, differentiate it again, and it will be like 2x or something?
Good point, good point. So let's do it with another example. Can I just quickly, yeah, I think I can get away with this. Okay, so what about if I gave you something like this?
X cubed.
Yeah, I'm trying to make it relatively nice. In fact, let me just write it down quickly. I want x squared plus 1. So I want this to be, yeah, 3x squared. 6x plus 3. Okay, so let's have a look. So we're going to go plus 3x squared plus 3x plus 4. Okay, so that's my working note. Okay, so let's imagine, really good question, let's imagine this was the curve. And I first of all want you to find the stationary points. You know how to find the stationary points, how do I do this?
Differentiate.
Okay, so to find the stationary points I need to differentiate. What do I get?
3x squared.
Yeah.
Plus 6x.
Yeah.
Plus 3.
Plus 3, perfect. To find the stationary points, what do I do to this gradient function?
Equals 0.
Set it equal to 0. So 3x squared plus 6x plus 3 equals 0. Have a look. Can I divide through by any common factor?
3, yeah.
3. So therefore this equation effectively becomes like this. How do I factorise that?
X plus 1 times x plus 2.
X plus 1.
Oh, plus 1.
Yeah. So x plus 1 all squared. Okay. So that means that x has got to be equal to negative 1. So in this case, I only get... that's not going to work, is it? Actually, that's a good point. Okay, so it's happened. I wasn't anticipating this. I should have thought about it. this has only got one stationary point. Now have a think, with this, it's a cubic function, how many stationary points am I expecting?
Yeah, it's supposed to be 3.
It's supposed to be 2 stationary points. Okay, so there's something weird going on here. Let's keep going. Let's keep going. Okay? Because it still illustrates the point. So, if I want to find whether it's a maximum or minimum, what should I do to this?
Differentiate the derivative again.
Exactly, I should just differentiate again. So I take this, differentiate it again. What do I get?
The 6x plus 6.
6x plus 6, okay? Now you're right, this is weird, because here, or sort of over here, I just end up with a number. And I just said, is that positive or negative? But now I end up with a function in terms of x. That's okay though, isn't it? Because don't I have an x value that I want to stick in? -1, okay? So I say, right, okay, at x equals -1, what's the value of my second derivative?
0.
It's equal to 0, isn't it? -6 plus 6 is equal to 0. Huh. Let's have a look over here. Well, I have a situation when it's positive, means it's a minimum. I have a situation when it's negative, it's a maximum. I've got neither of those, it's equal to 0. It's equal to 0. Can anybody think? Can anybody think what type of stationary point is this then? It's not a maximum, it's not a minimum.
A median.
Sorry? Yeah, kind of. So if anybody actually sticks this function into their calculator or into a computer or something, they should end up with a function that looks like this. Okay, it looks like this, right? This isn't a maximum, this isn't a minimum. In fact, the stationary point will occur at that bit there, where the function has a little bit of a break, has a little bit of rest. Because you're happy the gradient is still 0.